Have you ever used Google Maps to find the fastest route to your destination? Or wondered how logistics companies plan the most efficient delivery routes? These are everyday examples of a fundamental problem in computer science, finding the shortest path between 2 points. This problem arises in various fields from transportation and logistics to network routing and robotics. And at the heart of many solutions lies a powerful algorithm called Dijkstra's algorithm. Dijkstra's algorithm, named after its creator Edsger W. Dijkstra, is a graph search algorithm that solves the single-source shortest path problem for a graph with non-negative edge weights. In simpler terms, it helps us find the shortest path from a starting point to all other points in a network, where the connections between points have associated costs or distances. Imagine a network of cities connected by roads, with each road having a certain length. Dijkstra's algorithm can be used to determine the shortest route from one city to all other cities in the network. This algorithm is crucial for numerous applications, making it a cornerstone of computer science. In the following sections, we'll delve deeper into Dijkstra's algorithm, understanding its workings, applications, limitations, and alternatives. By the end, you'll have a firm grasp of this essential algorithm and its significance in solving real-world problems. In the realm of computer science, algorithms reign supreme. They are the step-by-step instructions that power our digital world, solving complex problems with remarkable efficiency. Among these algorithmic heroes, Dijkstra's algorithm stands tall, renowned for its ability to navigate networks and pinpoint the shortest paths. Dijkstra's algorithm, at its core, is a greedy algorithm. It makes locally optimal choices at each step, hoping to find the globally optimal solution. It starts at a designated source node and explores the graph step by step, always choosing the edge that leads to the nearest unvisited node. This algorithm is essential for a myriad of reasons. Firstly, it guarantees the shortest path from the source node to all other nodes in the graph, provided the edge weights are non-negative. This guarantee is crucial in applications where finding the absolute shortest path is critical, such as in network routing protocols. Secondly, Dijkstra's algorithm is relatively easy to understand and implement. Its elegance lies in its simplicity, making it a favorite among programmers and computer scientists. Finally, its versatility allows it to be applied to a wide range of problems beyond traditional shortest path finding, including geographical mapping, robotics path planning, and even social network analysis. Now let's unravel the inner workings of Dijkstra's algorithm. To understand its elegance, let's break down the process into simple steps. Imagine a graph representing a network of cities connected by roads, with each road having a distance associated with it. Step 1. Initialization. We begin by selecting our starting city, the source node, and assigning it a tentative distance of 0. All other cities, the remaining nodes, are assigned a tentative distance of infinity. This signifies that we don't know their distances from the source yet. Step 2. Visiting neighbors. Next, we visit all the neighboring cities of our source city. For each neighbor, we calculate the distance from the source to that neighbor via the connecting road. If this calculated distance is shorter than the neighbor's current tentative distance, we update the neighbor's tentative distance with this new, shorter distance. Step 3. Marking the visited. Once we've considered all the neighbors of the source city, we mark the source city as visited. This indicates that we've found the shortest path from the source to itself. Step 4. Selecting the next city. Now, we select the unvisited city with the smallest tentative distance. This city becomes our new current city. Step 5. Iteration. We repeat steps 2 through 4, visiting the neighbors of our new current city, updating their tentative distances, marking the current city as visited, and selecting the next unvisited city with the smallest tentative distance. Step 6. Termination. This process continues until we've visited all cities in the network, or until we've reached our desired destination city. Section 4. Real-life applications, from Google Maps to network routing. Dijkstra's algorithm's impact extends far beyond the realm of theoretical computer science. Its real-world applications are vast and varied, touching upon aspects of our daily lives in ways we might not even realize. One of the most prominent examples is its use in navigation systems like Google Maps. These systems utilize Dijkstra's algorithm to determine the shortest and fastest routes between locations, considering factors like distance, traffic conditions, and road closures. In the world of computer networks, Dijkstra's algorithm plays a critical role in routing protocols like OSPF, or Open Shortest Path First. These protocols employ the algorithm to find the most efficient paths for data packets to travel across the internet, ensuring that our online experiences are seamless and fast. Logistics companies optimize delivery routes using Dijkstra's algorithm, minimizing transportation costs and delivery times. Similarly, airlines use it to plan flight paths, considering factors like fuel efficiency and air traffic control. In the field of robotics, Dijkstra's algorithm enables robots to navigate complex environments autonomously. Robots use the algorithm to plan their paths, avoiding obstacles and reaching their targets efficiently. Even social networks benefit from Dijkstra's algorithm. Social media platforms can utilize the algorithm to suggest friends, identify influencers, and analyze the spread of information within their networks. These examples highlight the pervasive influence of Dijkstra's algorithm in our increasingly interconnected world. Section 5. Limitations. When Dijkstra's algorithm falls short. While Dijkstra's algorithm is a powerful tool for finding shortest paths, it's not without its limitations. Understanding these limitations helps us identify scenarios where alternative approaches might be more suitable. One of the primary limitations of Dijkstra's algorithm is its inability to handle graphs with negative edge weights. The algorithm relies on the assumption that moving to a neighboring node always incurs a non-negative cost or distance. In graphs with negative edge weights, this assumption breaks down, and Dijkstra's algorithm may fail to find the correct shortest path. While efficient for moderately sized graphs, Dijkstra's algorithm's performance can degrade when dealing with very large graphs, especially those with a dense structure. This is because the algorithm explores all possible paths from the source node, which can be computationally expensive for large networks. Dijkstra's algorithm assumes a static graph, where edge weights and node connections remain constant. In dynamic environments where the graph structure changes frequently, such as in real-time traffic updates or network routing with fluctuating bandwidths, the algorithm needs to be rerun whenever a change occurs, which can be inefficient. Dijkstra's algorithm doesn't incorporate any domain-specific knowledge or heuristics about the problem. It explores the graph blindly, which can be inefficient for problems where additional information could guide the search towards the goal more effectively. Despite these limitations, Dijkstra's algorithm remains a valuable tool for a wide range of shortest path problems. However, recognizing its limitations allows us to make informed decisions about when to employ alternative approaches. Section 6. Alternatives. Exploring other pathfinding techniques. When Dijkstra's algorithm falls short, several alternative algorithms and techniques can be employed to tackle shortest path problems, each with its strengths and weaknesses. The Bellman-Ford algorithm handles graphs with negative edge weights, overcoming one of Dijkstra's algorithm's limitations. It works by iteratively relaxing edges, eventually converging on the shortest paths. For problems where additional information or heuristics are available, AIsearch offers a more informed approach. It uses a heuristic function to estimate the distance from a node to the goal, guiding the search towards the most promising paths. The Floyd-Warshall algorithm computes the shortest paths between all pairs of nodes in a graph. It's particularly useful when we need to know the shortest paths between all possible pairs of locations, such as in a transportation network. For sparse graphs with negative edge weights, Johnson's algorithm provides an efficient solution. It transforms the graph to eliminate negative edge weights and then applies Dijkstra's algorithm to find the shortest paths. The choice of the most appropriate algorithm depends on the specific characteristics of the problem, such as the presence of negative edge weights, the size and structure of the graph, and the availability of heuristics. Section 7. Conclusion, the end of the journey, for now. As we conclude our exploration of Dijkstra's algorithm, we've journeyed through its inner workings, marveling at its ability to navigate networks and pinpoint the shortest paths. We've witnessed its real-world impact, from guiding our commutes to shaping the flow of information across the internet. And we've acknowledged its limitations, understanding that no single algorithm reigns supreme in all scenarios. Dijkstra's algorithm, with its elegance and efficiency, has earned its place as a cornerstone of computer science. Its impact extends far beyond the realm of theoretical algorithms, shaping the way we navigate our world and interact with technology. So the next time you use Google Maps to find the fastest route or marvel at the seamless connectivity of the internet, remember Dijkstra's algorithm, the silent force guiding you towards your destination. What other real-world problems can you think of that could be solved using Dijkstra's algorithm or its alternatives? The possibilities are limited only by our imagination.